Welcome to lecture 33 of Plant Design and Economics. We will continue our discussion on attainable region for chemical reactor network synthesis for complex reactions. In the previous lecture, we have introduced some general properties and general characteristics of attainable region. In today's lecture, we will first consider only PFR and CSTR and see how to construct attainable region for these reactors, and then we will consider a simple example to demonstrate the applications of attainable region. So, this will be our today's topic. We will first talk about attainable region for only PFR, then for only CSTR, and an example on manufacture of maleic anhydride will be taken last as an example of application of attainable region. So, we will consider Van de Vusse reaction scheme to demonstrate the application of attainable region. Now, this is a well studied reaction mechanism, and this represents a reaction network for which it is not easily possible to find out what will be the optimal structure for this reaction, because a plug flow reactor will maximize the amount of B produced in the first reaction, whereas a CSTR will minimize the amount of A consumed in the second reaction. So, we will consider this reaction to demonstrate the application of attainable region. So, the reaction scheme is given. It is basically a parallel decomposition. Note that A to B reaction is reversible. The rate expressions are given, and also at a particular temperatures the values of rate constants K1, K2, K3, K4 are given. Initial conditions are given, where you see that the starting mole of A is 1 kilomole per meter cube, and initially no amount of B, C and D are present. Now, we will first consider the case of plug flow reactor. So, let us first start with model equation of plug flow reactor. The mass balance equation for a plug flow reactor at unsteady state can be written as this. Note that at this stage it is basically a partial differential equation, as there is dependence of two variables, both time and volume. So, at steady state we can draw the dCA dt term. So, this becomes my steady state differential equation representing a plug flow reactor. Now, let us introduce the definition of space time, which is reactor volume divided by the volumetric flow rate. So, introducing the definition of space time, this differential equation can now be written as this dfa d tau equal to R A into V 0. Note that for constant density fluid flow, dfa will be equal to V 0 into C A, and then for steady state plug flow reactor with constant volumetric flow rate, we get the well known differential equation d C A d tau equal to R A representing plug flow reactor operation. Note that if you have catalyst pellets in the reactor, for example, a packed baked reactor can be modeled as a plug flow reactor. So, we can write the space time tau as weight of catalyst divided by the volumetric flow rate. So, let us now focus your attention on this equation d C A d tau equal to R A. So, we will make use of this equation. So, consider the Van der Waals reaction scheme again. We have just seen that the steady state plug flow reactor with constant volumetric flow rate, we can write d C I d tau equal to R I for any ith species. So, now look at the Van der Waals equations. We have 4 species A, B, C and D. Let us now consider my objective is to maximize the amount of B. Now, I write equation d C A d tau equal to R A and d C B d tau equal to R B. So, I get these two expressions from my rate expressions given. Now, if you look at these two equations, in the equations for d C A d tau and d C B d tau, the species concentration of C and D, they do not appear. So, it is possible for me to represent these systems in 2 dimensions, that is on the concentration space C A versus C B. So, to observe the path of a plug flow reactor with variable resistance time for a given feed concentration, all we need to do is we have to solve these 2 differential equations. And if we do that, let us say I have obtained these profiles for all the components A, B, C and D. For this, you also have to write the differential equations for species C and species D. But now, let us focus your attention only the profile for A and B. Now, these 2 trajectories represent how the concentration of A and B vary with respect to tau. So, these 2 trajectories will allow me to pick C A, C B values corresponding to various residence times and make a plot on C A versus C B concentration space. So, this is what we have done here. To observe the path of this plug flow reactor with variable tau and a fixed feed concentrations Ca0 Cv0, we have solved the ordinary differential equations from the feed point. So, the initial condition here is Ca0 equal to 1 kilomole per meter cube and Cv0 equal to 0. You can continue your integration of these differential equations up to the point where complete conversion of A takes place or up to the point of equilibrium. Then we make this CACB plot. Now, let us examine if rate vectors outside the attainable region point back to it. So, we look for non-convex regions on the curve that I have obtained for the plug flow reactor. For the given figure, we consider the tangent line passing through the feed point 1 0. We clearly see the presence of non-convex region. So, I can extend the obtained region by mixing. So, we expand the attainable region as much as possible with straight line arcs that represent mixing of reactor effluent and the feed streams. So, you consider this point and draw a straight line arc to the feed point such that you can extend or expand the previous attainable region or the candidate for the attainable region to the maximum extent that is possible. So, now we get, after joining this straight arc, maximum feasible space concentrations using plug flow reactor and a bypass, because any point on this straight line arc can be obtained by mixing these condition and the feed point. So, effluent represented here with the feed stream. So, maximum feasible space is now obtained using plug flow reactor with a bypass. So, beta is the mixing fraction. So, how do I obtain the bypass fraction beta? This can be obtained by writing down simple mass balance equation. My feed point is pure A. So, concentration at feed point is Ca equal to 1. Let us consider this point representing plug flow reactor effluent, where Ca equal to 0.2187. Now, consider this point which has Ca equal to 0.72. So, how do I obtain this point? What is the corresponding mixing fraction beta? So, we can write 0.72 equal to beta into 1 plus beta into plus 1 minus beta into 0.2187. You can solve this equation and you will obtain beta equal to 0.64. Similar equation you can also write for concentration of B. Now, let us consider a similar situation with only CSTR. So, what is the attainable region for only CSTR? Again we will start with model equations for CSTR. So, let us first write down the differential equations for CSTR where this van der Waals reaction is taking place. So, consider the schematic of the CSTR shown and then let us write down the mass balance equations. So, which is the rate of change of concentration of A is equal to the term which indicates the amount of A entering to the reactor FCA0, the term representing the A leaving the CSTR and then the reaction term. Similar equation you write also for species B concentration. So, you can rearrange this equation assuming constant volume, the volume can be taken out from the integral and we can divide both the differential equation throughout by volume V. So, this allow me to introduce the definition of the space time tau and now I can write these two equations. Now, I apply this for steady state. So, I draw the dCA dt and dCB dt and obtain the two algebraic equations for CSTR at steady state. So, these two equations will tell me for a given value of space time tau what will be the concentration of A and concentration of B given the feed concentration CA0, CB0. I have pure feed, so CA0 equal to 1 and CB0 equal to 0. So, upon specification of a feed point CA0, CB0 in this particular case 1, 0 and CSTR residence time tau, a CSTR effluent concentration can be obtained. CSTR effluent concentration will be indicated by the concentration vector CA, CB. Specification of a different feed point or different space time will result in a different value of the concentration vector C. Note that the concentration vector is a vector with two components CA and CB. Plug flow reactor operates over a range of achievable concentrations, but the CSTR operates at distinct concentrations for a fixed feed point and tau. So, there is a difference between the plug flow reactor trajectories and the CSTR trajectories. The CSTR operates at distinct concentrations for a given feed point and tau. So, we specify a range of CSTR residence times for a common feed concentrations and solve for the corresponding CSTR effluent concentration C. recall how we obtain the PFR trajectory. We just solved the differential equations, two differential equations representing the PFR. The independent variable for those differential equations was tau. Now, to obtain the similar trajectory for CSTR, we specify a range of CSTR tau for a given feed concentrations and solve the two equations, algebraic equations, to find out CACB, which represents a CSTR effluent concentration. So, when a collection of such CSTR solutions for a fixed feed is plotted in a phase plane CACB, each point on the profile indicates a physically different CSTR scenario corresponding to a unique residence time tau. The collection of CSTR points for a range of residence times is referred to as CSTR locus. So, the collection of these CSTR points for a range of residence times tau will be known as CSTR locus. So, this is the figure which shows you the PFR trajectory as well as the CSTR locus. So, they are obtained for the same reactions, Van der Waals reaction scheme, same kinetics, and also the same feed point 1, 0, Ca equal to 1, Cb equal to 0. The end result appears similar, but the information represented by the two profiles is quite different. What is the difference? The PFR produces a continuum of solutions for a fixed feed and reactor volume, but the points on a CSTR locus corresponds to a physically distinct scenario in the CSTR. So, to obtain the CSTR locus, we solve these two CSTR steady state equations for range of values of tau, and we have plotted CACB values on the concentration space Ca versus Cb, and we have obtained this feasible region. So, this is the candidate region for attainable region for only CSTR. So, again we have to check whether this region can be enlarged upon mixing or not. So, is there presence of non-convex region? Yes, it is. So, there is non-convex regions and mixing can enlarge the attainable region. So, we join the feed point, we say this point with this straight line arc, and this clearly indicates that mixing enlarges the attainable region. Again, the mixing fraction alpha can be obtained using simple mass balance equations, Lieberman rules. Now, we will consider the reactor network synthesis for manufacture of malic anhydride. Malic anhydride is manufactured by the oxidation of benzene with excess air over vanadium pentoxide catalyst. The reaction scheme is shown here as a collection of 3 reactions. In reaction 1, benzene reacts with oxygen to produce malic anhydride, carbon dioxide and H2O. Reaction 2, malic anhydride reacts with oxygen to give CO2 and H2O. Reaction 3, benzene reacts with oxygen to produce carbon dioxide and H2O. Now, air is supplied in excess. So, this reaction scheme can be approximated using first order rate laws. So, this reaction scheme as shown in reaction 1, reaction 2 and reaction 3 can be represented approximately by first order rate laws A to P to B and A to C. The rate expressions are given R1 equal to K1 into Ca, R2 equal to K2 into Cp and R3 equal to K3 into Ca. The rate constants are given as a function of temperature. My desired product is malic anhydride. A represents benzene, the reactant, P is malic anhydride and B and C are byproducts CO2 and H2O. Note that oxygen is present in excess. All the rates have the units of meter cube per kg catalyst second. So, desired product malic anhydride, the corresponding rate constant is K1. So, the definition of the problem is as follows. Given the available feed stream containing benzene at concentration of 10 mole per meter cube with a volumetric flow rate of 0.0025 meter cube per second, propose a reactor network of isothermal reactors to maximize the yield of malic anhydride. You can note that feed is largely air. So, to solve this, first we need to fix an appropriate reaction temperature. We make use of one heuristic that we talked about in our very early lectures. For competing reactions both in series and parallel, adjust the temperature, pressure and catalyst to obtain high yields of the desired product. In the initial distribution of chemicals, assume that these conditions can be satisfied. Before developing a base case design, obtain kinetics data and check this assumption. So, for various values of temperature, I plot how the rate constants K1, K2, K3 vary. We are interested in the desired product malic anhydride and the corresponding rate constant K1. The plot is 1 by T in Kelvin versus log of rate constants K1, K2, K3. So, we see that in the range of 366 Kelvin to 850 Kelvin, the rate coefficient of the desired product K1 is larger compared to other rate constants K2 and K3. So, an operating temperature at the upper end of this range is recommended as the rate of reaction increases with increase in temperature. Now, you look at the reaction scheme. All of the reaction rate expressions involve only benzene and malic anhydride, Ca and Cp. So, this allows us to represent the system on a two-dimensional concentration space of Ca versus Cp, concentration of benzene versus concentration of malic anhydride. Reaction is carried out in a packed bed reactor, and we have catalyst. We will model it as plug flow reactor. So, we start by tracing the composition space trajectory for a packed bed reactor, which is modeled here as plug flow reactor, which depends on the solutions of the molar balances. So, we have to write down the differential equations representing the packed bed reactor, which is being modeled here as plug flow reactor. We discussed that dCi d tau equal to Ri is obtained for plug flow reactor. This is catalyzed reactor. So, the space time tau we can write as W by V0. So, then note that this can be written as V0 into dCi dW. So, let us write those differential equations for Ca and Cp. So, basically we are writing V0 dCa dW equal to Ra and V0 dCp dW equal to Rp. So, to obtain the PFR trajectories, we just have to solve these two differential equations with initial conditions for Ca and Cp. Now, we obtain the trajectories by solving the mass balance equations for various operating temperatures, for example, 600, 700, 800 and 900. These trajectories are convex and the rate vectors computed along their boundaries are tangent to them. So, we can conclude that each trajectory bounds the attainable region for its corresponding temperature. So, we have obtained our attainable region. These cannot be further expanded. So, we have obtained for individual temperatures the attainable region for the packed bed reactor, which is being modeled here as plug flow reactor. So, a single plug flow reactor provides the maximum production of malic anhydride here. So, what will be the desired space velocity? The desired space velocity is that which brings the value of Cp to its maximum value. So, you have to obtain tau corresponding to these maximum values of Cp. Now, let us look at the two trajectories corresponding to 800 degree Kelvin and 600 degree Kelvin. For 800 degree Kelvin, the maximum concentration of malic anhydride is 3.8 mole per meter cube. and catalyst required is 4.5 kg. Whereas, at 600 degree Kelvin, the maximum concentration of maleic anhydride is 5.3 mole per meter cube, but catalyst required is very high, 1400 kg. So, with increase in temperature, the catalyst required is less, but the maximum concentration of maleic anhydride decreases. So, a compromise is required, and a good compromise is to operate the packed bed reactor at an intermediate temperature, let us say 770 degree Kelvin, which will correspond to a maximum concentration of maleic anhydride of 4 mole per meter cube, and this will require 8 kg of catalyst. This figure shows composition profiles for all species as a function of weight of catalyst, which is also basically proportional to the bed length, and this figure corresponds to the temperature 770 Kelvin, which we considered as a best compromise temperature. Now, you can note that the optimum catalyst loading, where the concentration of maleic anhydride is maximum, is about 8 kg. For this isothermal operation at 770 Kelvin. Finally, we make a plot here of yield and selectivity versus weight of catalyst. Yield is defined as desired product rate divided by feed rate, whereas selectivity is defined as desired product divided by total product. Look at the figure. The yield at 770 Kelvin and 8 kg catalyst, that is the condition that we have chosen, is 61%, while the selectivity is only 10%. Why the selectivity is so low here? The selectivity is so low because the production of the large amount of byproducts CO2 and H2O. So, here we learned how to obtain the attainable region for a simple example of production of maleic anhydride. It was possible to obtain the attainable region with a single plug flow reactor. In the next class, we will look at a more involved example where the attainable region will be obtained by combinations of plug flow reactor, CSTR and mixing of steps. With this, we stop our discussion here.